And thank you very much for having me as a speaker today. I really appreciate that. And then as I sort of provided this talk title, and then I realized that's not kind of sort of, resources aren't kind of sort of what we're talking about today. So I'm going to talk about some of the same things, but really I'm going to focus on what I think is important to understand about the data, because all of us are going to subsequently, for the rest of the day, talk about how we're going to use that data and all the algorithms and fun and targeting and all the other things we're going to do with it. So understanding the data, and I want to say the consequences, really comes down to things like talking about precision and accuracy, which, you know, we all go, oh my goodness, she's going to show those bullseyes again. So I'm long done with the bullseyes to explain precision and accuracy, but I do use kittens. So the kittens, in this case, do I have a pointer?
Yes. Yes.
Yeah, that's the pointer. So the idea with the kittens is to just remind people accuracy and precision are different concepts. Accuracy would say, well, the mittens are all about the same distance from the kitten's paw. So that could be accurate data, perhaps not precise. And then you can have very precise data. So the kitten's mitten is always in the same place, but he's pretty far off of his paw. It's not really doing him much good. So how do these two different concepts affect how we can use data? So accuracy. Accuracy, I think, is the easy one. I think we've come a really long way in the industry in the last 15 years. Thank goodness for 43101. All of a sudden, everybody went, oh, I'm supposed to do quality control. Who knew? And so we've really been holding the commercial labs to account. We put in a lot of quality control materials. We make Short charts. If you're not making Short charts, we have a free Excel macro. And you're more than welcome to have a copy, and it will generate for you very quickly all kinds of statistics and charts for as many elements as you care to plot. And do it often. And of course, the other thing that's developed in at least the last 10 years, there's a wide variety of very high quality reference materials. Yes, I happen to be a distributor of some of the best. But besides that, there really is a lot of opportunity to do accuracy well. And I think that as an industry, we've really pulled up our socks, and we're really moving towards doing a good job of maintaining high quality accuracy. Now, maybe we're having a bit more trouble still with precision, because precision really is more complicated. It does impact all kinds of decision making we have, whether it's evaluating geochem anomalies, discriminating ore and waste, evaluating bias. There's all kinds of different stages of the work that we do where the numbers we're looking at are not really, we haven't assigned the plus or minus, the uncertainty, the error. And it's actually partially because we do everything in a sort of Excel spreadsheet-based environment, and we have to put a number in each one of those cells, and it's just really hard to do that with a plus and minus attached. And just to give you an example of why sometimes this is important, and I do a lot of work around gold, and so gold is often where you have these kinds of precision issues. But here's an example. So there were 3 samples, A, B, and C. They were collected at the Bulyanhulu mine a long time ago, and there were large samples. So they're more in the order of 30 kg, and we did what we called an assay to extinction experiment. And so the yellow dots in each case for those samples is the average. That the point is, even though the average of, and I don't, if you don't know Bulyanhulu, it's got a grade of about 17 to 20 grams per ton gold, depending on who you talk to. So each one of the subsamples was analyzed by screen metallics. And you could get any number essentially from 0 to 110 grams per ton out of the same sample. And every single one of those numbers is correct, right? This is not an assay problem. This is not the lab making a mistake. This is really and truly the kind of distributions we can get for a single sample. And what we try and do when we're talking to somebody about precision is we're trying to communicate really what the risk factor is when I give you a number of 5 grams per ton, and I'm trying to tell you, well, in fact, I know that number could be anywhere from 2 to 10. And that's what we're trying to do, and we're trying to, in large groups, in large data populations, give some kind of a summary of what we actually expect the repeatability to be of any particular number. Now, we have a bit of a problem that was identified by Cliff Stanley and Dave Laurie in their paper in 2008, that if you do something like read through a bunch of 43101s, you see all kinds of way cool statistics that are quoted to try and explain precision. Again, we're just trying to communicate these things. There's a whole variety of these mathematical expressions which are not the same thing. So we have to be very careful if you say my project's got X and my project's got Y, that we're actually even talking about the same kind of numbers. Now what Cliff Stanley and Dave Laurie suggested was to use coefficient of variation with one caveat, that you are supposed to have thousands of data points, which can be a bit of a challenge. And then the other part, I think that we've been missing a little bit on the communication, and then I have to give ALS credit for, and Michelle is sitting over there, so we can thank her for the slide, where we have precision on the y-axis and goal concentration on the x-axis. And the point of this is that it's not surprising, every single measurement system, your precision is poorer as you approach the detection limit. And in fact, for a chemist, if you said, what's the definition of a detection limit? More or less, what they're trying to tell you is that somewhere around the detection limit, I think that I can distinguish signal and noise, maybe. I think it also has something to do with what your competitor put in their fee schedule, but that's okay. The point is, at the detection limit does not mean that we have the best possible precision. Precision falls apart asymptotically as we approach the detection limit. It's really only once we get 20, 25 times higher than the detection limit that we start to get, okay, don't do that. We start to get close to what the optimum precision is. So the optimum precision might be 7 to 10% for a fire assay, and we don't get anything like that. We get a precision is closer to 100% when we're at the detection limit. So there's this other added factor, that precision changes with concentration. Let's make it a little bit more difficult, because when we talk about precision, we really need to know the precision of what. So sampling errors are cumulative. And what I try to explain is that, for example, if I'm looking at 2 halves of the drill core, I'm not really talking about the uncertainty with sampling those 2 halves. I'm really talking about, I took the 2 halves of the core, then I crushed them, and then I split out some aliquot, and how I split that out puts in some uncertainty, adds to my precision measurements. And then at the lab, again, they take an analytical aliquot, it might be 50 grams for fire assay, and it might be 0.2 grams for your ICP analysis. So all of these things, in addition to your geological uncertainty, it's going to impact the total precision that we measure for some of these things. And then the question is, how does that going to impact our data, of course? So sometimes I do calculate coefficient of variance, and I do find that a useful statistic, and you'll see some graphs here showing that. But often what I'm doing is I'm trying to communicate to the user that what the risk is when they make decisions based on a single data point. And that's why we rarely do, right? We're usually looking at very large groups of data from drill core programs or large soil sampling programs. But the point here would be, for example, I would show the relative percent difference. So that's just the 2 assays divided by the average and plotted against the average on the x-axis. And what you see is between 0.1 and 1 gram per ton, most of the results fall within plus or minus 50%. In fact, if you calculate the precision using the CV, it comes out to be 40%. Everything lower than 0.1 starts to fall apart a bit. You can see those lovely sort of sun rays that emerge to the left, and that's primarily a function of the data. Because at the very low end, there's only so many combinations and permutations of 0.01 minus 0.02, 0.02 minus 0.03, so you get that artifact of the data. And that tells you just that that's where your detection limits are. But what's important is it changes with concentration, just as was predicted in the analysis shown by at the LS slide. Now here's something just slightly different, which is the prep duplicates for the same project. So the first slide was just comparing two assays of the same pulp, and now I'm showing for the same project the assays from two different splits of the course. The precision is a little worse in that same grade range, 0.1 to 1 gram. But you have to remember that that precision of the prep duplicate analysis includes the, let's call it, error associated with taking the sample of the course material plus the inherent sampling of the pulp, right? Because I've actually done 2 steps to get to these numbers. So it's a combination, it's cumulative. So, in fact, in this particular case, and I use this case because it's a particularly egregious case of a nuggety effect for a low-grade deposit, even if you did something extraordinary like double the cost of doing sample prep for the course, maybe you crushed it finer, maybe you took an even larger cut, you wouldn't necessarily solve the problem because you still have very noisy assays on the pulp. So, this is, to me, is an example of really understanding where the precision, measuring the precision throughout all the processes and understanding perhaps what solutions you're going to have to use based on the data. Fundamentally, if you don't measure it, you can't fix it, a fundamental saying. So again, I just am showing you another case of similar data, 4,500 lab duplicates, so you can tell this was a rather large data set. And again, this time I'm showing on the y-axis the CV percent, I'm showing the average gold on the x-axis. And what I would do is I would calculate the precision for different grade levels. And if I just calculate the precision for all of the data, I would be telling you the overall precision is 28%. And you would go, oh my goodness, that means all my numbers, I can't trust them. They're all going to be more or less plus or minus 30%. How will I ever make sense of that? But in fact, that's not the case. And you need to talk about the precision at different concentrations. So the concentration, the precision as low as 9% for greater than 2 grams per ton gold, and 9% is more or less in the range that the laboratories quote for the fire assay method on perfectly homogeneous materials, right? 7 to 10%. And then, of course, the precision gets worse as you approach the lower concentrations. And there's a big difference depending on what the concentration level is. Now, those were gold examples. And gold is a big part of the overall mineral exploration budgets worldwide, but you should be very thankful if you're working on a base metal project because this is an example for an Arizona copper project. And here you'll see on the y-axis, I don't have plus or minus 100%. Really, almost everything falls within plus or minus 5% for the pulp duplicates, and certainly not much worse than plus or minus 10% for the pulp prep duplicates down to very low levels. So it's not it's a problem only for some projects and some elements. And some of the things we do with the data is, of course, we make lovely maps. We plot all the data. We interpret all the trends. And of course, anybody who knows me knows that the next point is that this is random data. And it's really important that some of our problems with data with poor precision may be problems with accuracy, differences between batches. We can end up with fundamentally what looks like random data, and we could certainly have a great deal of fun interpreting it. And anybody who has an interest in this, and who may have missed this, Dave did a talk, I think, in Chile. And I'm sure this is on the IDMEX website. But he has a great way of talking about the importance of how you interpret trends, understanding the importance of how the mind works, and the fact that we are always looking for patterns. And some of the things that we get asked to do on a regular basis that isn't necessarily apparent to everybody is the fact that we're always looking to try and looking for bias. Important part of our job, and it is affected when we have imprecise data. When the data are noisy, it can be very difficult to determine whether two different data sets are the same or different. It's a little bit one of those Sesame Street things, right? One of these things is not the same. We might be asked to compare analytical methods. So is the Acarija copper the same as the XRF copper? It doesn't matter if I took a 250-gram subsample for my prep versus 1,000 grams. I did check assays. I have core duplicates. I might be asked to twin drill holes. And we have some difficulties because perhaps of a lack of understanding of how some of the statistics work and issues around precision on being able to actually do this properly. So the reason for my rant this morning, in case you're wondering, is I found again in another 4310 report that somebody has two columns. Here's some data, data set A, data set B. I've calculated the averages, and the difference between the averages is 20%, therefore there's a 20% difference, and you can't compare averages. And there's a whole bunch of reasons for this, but one of them is things to do with standard deviations. And the fact that most of the data sets we're confronted with are non-normal distributions. So here is a cartoon from some Australian friends. Funnily enough, it's about drunks, but I'm not going to make any comments about that. The point is, if the drunk, on average, walks down the center line of the highway, he is perfectly safe. If at any point, though, the drunk wanders on and off the center line with some plus or minus, some precision value, he's constantly getting hit by some vehicle and he's dead. So it's really important to understand the difference between talking about averages and talking about a number and its plus or minus. But there's a lot of cases where averages are not going to do the trick, and we have to really be aware of this when we're looking for bias. And in addition, there are other sneaky bits that fall into the problem when we're trying to assess bias. And one of these, again, seems to be quite reserved for the things that we are doing in our industry. And the one that concerns me at the current time is this concept that a lot of people, a lot of companies will have a rule. Well, they say, if my fire assays are greater than 5 grams, then you should automatically do a gravimetric finish fire assay. Or do a screen metallic, or maybe, who knows, a leach well, a bulk leach. The problem occurs when you start to do things like resource estimation and you say, well, I know that screen metallics are better than a 50-gram fire assay. Therefore, any time I have a screen metallic, I'm going to replace all my other fire assays. Okay? Very common. This is what we do. And there are consequences. So here's an older case when they were drilling off a Detour Lake. And there were over 2,000 samples where values by the 50-gram fire assay were over 5 grams, and this triggered the fire assay metallics, the screen metallics, whatever you want to call it. Now, here was the logic. The consulting group asked to do the resource calculation said, the 50-gram fire assays are twice as often higher than the screen metallics. Wow. I mean, that's not just off a little bit, right? That's off a lot. And I know that screen metallics are better than 50-gram fire assays. Therefore, your 50-gram fire assays are biased high. I won't use them. That was a problem because there was something like 50,000 samples with only 50-gram fire assays. All the other quality control, rigorous quality control program, didn't show there had been any issues. So what is the problem? The problem was only sending in samples with greater than 5 grams per ton gold. Because in fact, if you turn your head and you look at just the samples on the right side of the dashed line, you'll see there's actually, once we get over sort of 10 grams, there really is a pretty even distribution of samples that are positive and negative, that are, one is higher than the other. The problem is, we didn't submit the samples that were less than 5 grams per ton gold, and they would have, some of them would have come out higher. About 20% of them probably would have ended up higher. And if you automatically, in a case where there's poor precision. Okay, this only applies to very nuggety, difficult to sample ore bodies. You will underestimate your gold resources if you automatically use the screen metallics. I think we also are doing the same thing more subtly when you replace your 50-gram fire assay with an AA ICP finish with a gravimetric finish. Anytime we do this kind of selection bias, if you do it for your check assays, if you only check the highest grade samples, the results that come back will be biased low. Now, the only reason we pulled this out of the fire is there happened to have been another, it's actually about another 1,000 samples that were selected on a different criteria. Same project, same lab, but these samples were selected on the basis of there being visible gold. And when you did that, there was no bias, right? So you see that here's a plot of the screen metallics versus the fire assay gold, the X equals Y line, and more or less, things are balanced. It was not a 2-to-1 ratio as there was when we selected samples on the basis of grade. Now, how can we fix this sort of thing? It's really not hard. What Detour does now, they gave me this example from their last drill program, and they'll go into a mineralized zone, and all of the samples will be assayed for screen metallics. So here's where we have gold by 50-gram fire assay on the x-axis, screen metallics on the y-axis, and again, it's more or less even. We have 62 cases with screen metallics higher and 69 cases with the AA finish higher. And in this case, I would probably tend to select the screen metallics values because I'm using the fire assay AA finish really as a quality control measure for those values. Now, in addition to being aware of things like selection bias, are there other tools that we're going to be able to use, perhaps in the future, to help ameliorate problems we have around precision, in particular the small aliquots we may be relegated to for some of the test work? And we will talk about today, I'm sure, portable XRF, and that certainly offers a number of solutions. But here I just want to give you a couple of words about a relatively new technology. Well, it's certainly new for us in North America, although it's a photon assay method. It's been developed for over 15 years by CSIRO in Australia. What was new last year is that the very first commercial system was put in place in Perth. They have done tens of thousands, maybe not tens of thousands, maybe 10,000 samples. And the way it works is you can irradiate a relatively large sample of 500 grams or so, depending on the specific gravity of the material. It penetrates the whole volume, and it has very little matrix sensitivity. It is not neutron activation, and it is not regular XRF energy. So for me, the big advantage is the large sample size, relatively low matrix sensitivity, and the fact that the samples can be returned to the client. So what I like is that you could do this test and still do fire assay or metallurgical sampling or anything else that you need to do. Okay, so everything's got a limitation. Right now, the problem is there's only one unit in the world. It's in Perth. A second one has been shipped to Kalgoorlie, and a third is on its way to Kalgoorlie. So that's not great for projects in North and South America right now. It is something I think you should be aware of because it could someday be coming to a lab near you. Now, there are some tests that still need to be done because gold can be self-shielding. And there's some concern that gold particles greater than 100 microns might lead to lower values. And there are some interferences when you have hundreds of ppm of uranium, thorium, and barium, and there certainly are some geological contexts where that could happen. This is what it looks like. So the jars are on the right-hand side. They go on a conveyor belt. And somehow, even though there's nominal sample preparation and sample weighing, apparently you can still mix up samples. It's just a thing. And so they go on this conveyor belt into this magic box. It is not portable. It is something like, I think it's 6 meters by 6 meters by 2.5 meters tall. I'm really hoping someday they miniaturize this. That would be a great tool to put down a blast hole, but we're not quite there yet. And that's just one of the things I want to advise you about in terms of keeping your eyes open for new technologies. How am I doing?
Yeah. You got about 5 minutes.
No, you're going to have to really slow down because I'm going to have to answer questions otherwise. So what I was trying to imply today is that paying some attention to what actually happens to your samples when they get to the lab, how they're processed, how you're doing it yourself in the field, if that's what you're doing, being able to understand that precision changes according to concentrations, and this is true for all measurement systems, and that we really want to understand things like precision, how it might impact bias, how it might impact our ability to interpret the data. The one for selection bias is easy. It's just avoid selecting samples for additional assays only on the basis of other chemical analyses. And I like to always encourage everybody today, and certainly with a theme of innovation, to continue to use new technologies when appropriate. So thank you very much for your listening today.